Thank you. I appreciate the invitation, Professor Conrad, and it's my pleasure and honor to be here at the University of Houston. Thanks for the invitation, my pleasure. As Professor Conrad introduced me, I'm a bridge engineer by training, who happened to be a materials researcher. So a lot of times, as a structural and bridge engineer, I'm driven by a practical application or the need to solve a problem. And I do the materials research basically to solve this problem. So I'm going to talk to you about the topic as part of the work on ASCE. I'm the chairman of the ASCE Infrastructure Resilience Division. And for the last few years have been involved in work on resilience, which is basically a framework that relates to everything everyone here is doing. We are after, so that when we see disasters or issues, can address. So one of the topics I've been involved with is the area of emerging technologies, and which is basically the research we all are doing. This emerging technology that lead to emerging technologies that we would like to use to solve the current problems. And the biggest two problems we have, of course, one of them is driven by climate change. So that's where my talk is going to be evolving about. So I will talk about, let me just, okay. The concept of resilience at large, quickly, and climate change, talk about how do I see that emerging technologies would help on this for both resilience and climate change. Then I will dig in a little bit for some of the areas we worked on and resulted in some work. One of them is the major area now we've been working for the last 11 years, the area of sealing abandoned oil wells and using nanomodified polymers in that. And you will see most of my talk will evolve about nanomodified polymers for different applications, going between the application for the oil wells to applications in concrete, to applications in composites, for seismic, so a lot of it, but all driven by the interest in this new tool that I happen to find and be able to actually do a lot of use of it for different needs. I'll talk about new modified 3D printed polymer concrete we're producing and examining new nanomodified composites and nanomodified, something new we are doing with the Air Force Research Lab called Cognizant Composites. We'll talk about 3D printed viscous dampers and the roadmap as I see it for using emerging technology. So the two basic emerging technologies, and I think my abstract talk about this was the nanomodification and 3D printing. So resilience and its relation to climate change, you see here, of course, they're always in the news. Some of those sad events. We have floods that were in Pakistan a couple of years ago, Hurricane Katrina, Hurricane Harvey here. Yes, so a lot of these events that we all agree by now that they are driven by changes, whether they are human-based or not, but there are climate change we all see. Tsunamis, like the one that happened in Japan, result in big issues with the nuclear plants. In addition to this, we have other observations, and these observations here is in a case where this oil well happened to actually go on fire as well. That's not what we see typically. And you can see here, huge methane emission. What you actually see typically with methane emission, that many of those oil wells are in actually areas where there is vegetation and there is life in them. And when this methane emission happens, it kills everything around it. So methane emission is a huge problem happening, and it's one of the topics that's driving our research and the development. Now, with the definitions with the word resilience, people say resilience. What does resilience mean? What do you mean by having a resilient system? Is it good? Is it bad to have a resilient? What is resilience? So we basically talk in very simple concept, and we try to have some engineering application to it. So what the resilience we mean is a capacity of a system basically to absorb disturbance and maintain functionality. So you have a system of bridges here in Houston. Yes, you have a big hurricane, what you want to happen, and when that hurricane happens, they will maintain functionality and they will absorb that shock. And even if we have some failures, they will not result in complete collapse of the system. So functionality, you can have it, so you can actually restore the system. This definition of resilience have been defined by many researchers related to, we call it sometimes the 4R for resilience, which is the robustness, redundancy, and response and rapidity. Now, what is basically, imagine this is a system. What I'm showing here is the performance of a system. Think of any system, a bridge system, a building system, yeah, or a water system, yes? So it's functioning with time as you regularly, and as the functionality happens with time, the system functionality would drop because of aging, because of need for maintenance, yeah? As you make the maintenance, the system will go up again in performance and down and up and down. Typical, that's a standard. And then you suddenly have a shock to that system. So what happens when you have a shock, the system performance will significantly drop down, yeah? Now, if the system performance drop from here to the bottom, then the system collapses. There is no system, yeah? What we would like to have to see the drop and to have an immediate recovery that's due to the system redundancy. System have some other parts of it that was not used in the typical performance, yeah? But it's like your battery, yes, at the time when the light goes off, it goes on, yes? That is the redundancy. You get some functionality back. And then with time, you build a response and you go back to performance. Now, there is no guarantee you're going to go back to the old performance. You might go back to a lower performance, but you are performing back and the system, and you might go back to actually the old and the higher. Usually, the area under this curve is used to describe the quantity that is saying we call it resilience. So when you think of that mathematical definition, which could be argued on, but basically you can see that the recovery is a big part. How fast you recover and how far you recover is a good metric to describe resilience. So anytime I'm thinking of resilience, I'll be thinking of what can I add to the system such that it could recover fast, it can continue functioning, yeah, and recover well. So again, this is the 4 topics of resilience that we are after, and we combine climate change with it just because of the fact that we realize that many of those events are tied to climate change. So what we're thinking is these 4 R's, how to make them. So we're thinking that by using a lot of sensors and smart materials, we can provide enough redundancy and resourcefulness to the system, yeah? Because now we know how much aging is happening in the system. By providing advanced construction technology or technology like 3D printing, for example, we will be able to provide some rapidity to the recovery. And by providing other sensing technologies as I have here, like for example, the drones or any sensing technology, you're having a good awareness of the system performance, so you can actually try always to keep up to be able to withstand this shock. So this is just a conceptual idea of how those emerging technologies can be used. That I will be talking about some of them. So our goals basically in our research, my team at UNM is to engineer polymers, concrete, and composites with improved mechanical properties and capabilities, leading pathways to mitigate climate change and improve resilience. And we do this using nanomaterials, 3D printing, and smart sensing technologies. So these 3 things, what I call emerging technologies, integrating them together by sensing, by enabling nanomaterials to change or to allow it to control the material behavior, and by using 3D printing to actually enable print or construction at times or places that is not easy to happen. Then we can actually create a generation of materials, concrete and composites that can mitigate climate change and improve infrastructure resilience. So I'm going to start with a talk, about climate change, because it is dear and near to my heart, and because of the fact that I'm going to be involved more in the next at least 2 years through a startup company on this work. So basically, one big issue is that the issue of abandoned wells and orphaned wells and their emission. So there is a lot of documentation, but the real number, the full number of orphaned wells in the United States is, we call it work in progress. We do not know the exact number. There's a lot of orphaned wells. Orphaned wells, by the way, and there is those type of wells that operators has used them, and then these operators have went bankrupt, and they became back empty, yeah, and they are unplugged usually, and they are the responsibility of the government. This could be the federal government, the state government, or the tribal land, but it's nobody's well, yeah, and they are emitting methane. So how many of those do we have? That is work in progress. We know that there is currently about 100,000 of them in the US, and many of those orphan wells are unplugged. Okay, we care a lot about when we finish operation on an oil well, it needs to be plugged because otherwise there is the greenhouse gases that's going out of it. So many of them is unplugged. The EPA estimated that there is 3.1 million abandoned wells. Abandoned means they were operational and today they are not working. Okay, many of them plugged, many of them that is belonging to some entities and companies, some of them do not. But many of them actually leak, and leak greenhouse gas, especially methane. The traditional approach basically is to go and plug these wells with cement. And as you can see here, I'm just showing here, this is a schematic from publications by others. That's a typical well. Usually, as you know, and many of you worked in areas related to oil well cement, that you have the formation is bigger than the steel. So there is cement put here during operation. And we call this the annulus cement. And then, of course, because cement is a material that is porous and that actually is cracks and shrinks. So there are pathways for gases to go in the microannulus here. And later on, when we actually abandon the well, we go and fill it with this cement plugs. They are about 100 to 150 feet plugs, but they also are cement. And many times with time, they actually leak because of their service in very harsh service environments. So there is a need for alternative materials that whenever we see this case, that actually can plug the cements and prevent the greenhouse gases. So we needed to develop to stop methane emission. Methane, by the way, is 23 times worse than carbon dioxide. As if you look at the carbon equivalent. So every material has a carbon equivalent. So if you calculate carbon equivalent for CO2 is 1, for methane 23. And methane effect on the greenhouse gas is way higher, especially at the short term. So if we want to actually in 2030 drop the greenhouse gas emission, we have to tackle methane before CO2. So over the years and through research, we know that we need, Department of Energy announced that they need actually a high flowability subsurface sealant that can go and seal these micro cracks in the cement plugs and behind the well. And this needs to be an environmentally friendly subsurface sealant so that the material actually, when it gets, if it gets to the water, that it would not contaminate water or the subsurfaces. Need to have a high strength bond with cement and rock formation. And the criteria was actually to develop a material that can flow below 30 micrometer cracks, because that is where gas can flow. A lot of the liquids or the materials, the repair materials available do not flow. And it can be indefinitely, so have very high resistance to chemicals and provide basically a better seal. So we tackled this starting 2012. And we worked on materials. One of the materials we worked on, we have now about 3 of these materials, but one of them I'm presenting work here on, we published on this since 2017, is nanomodified MMA. And this material basically can flow below 30 micrometer cracks. So to test this, what I'm showing here, this is the bond strength test. This is shale and this is cement. We are simulating here that interface you see here, this interface here, yeah, between the cement and the rock formation. And basically we created it such that there is a gap around the shale of 30 micrometer. And we injected materials in this gap. And in this gap, we injected microfine cement. That is the typical material used today by the oil well industry, such that they can actually, they call it squeeze jobs. They squeeze the cement in it to close those cracks, yeah? And we used also some epoxies, that's standard epoxies, and we used the MMA, but we used actually our nano-modified MMA. And we injected them, and then we went and we did a push out test, as you can see here, to basically apply the force here and measure the bond strength and look at these cracks. And you can see here the displacement versus the load. You can see this is the case for microfine cement. It hardly carried any load, yeah, about 1 kilonewton or so. While here, the nano-modified MMA epoxy carried higher, Nano-modified MMA carried about an order of magnitude of the load. And much higher displacement, which means the material have a very important thing in repair materials, which being flexible. Yeah, so very high ductility material. So we went and tried to identify why did this happen? Why does we have a bond strength here of 6 megapascal compared to 0.6 or 0.5 megapascal with the microfine cement? So, and that's basically what we have here, yeah? We have this, we have the gap when we pushed it. We looked first at the contact angle of the materials, and we could see that the contact angle of the microfine cement with this water is about 74 degrees compared to the sealant we are talking about here, which is 27 degrees. Keep in mind that when the contact angle gets smaller, then the material has a higher affinity, which basically means the material can have higher wettability. So it can actually wet the surface. Push any material with lower wettability. So in many of these locations, you will have water, yeah? So when you push this material now with this low contact angle, it will push the water and fill the space. This is an interesting microscopic image where we actually show here the cement based against the shale. And this is 200 micrometer. This crack, again, we created it to be 30. We injected the microfine cement, but you can see at the microscope that actually there is a gap, yeah? Because the microfine cement cannot actually penetrate the gap. Compared to our material, what we did with our material, we actually have rhodamine, which has a color to it so that we can see where the material go. And you can see, interestingly, not only it fills the gap, but it actually impregnates both the cement and the rock formation. So the material actually expands to both sides. That's why it's able to seal very well. We did an interesting test to see, can it flow below 30 micrometer? And what we did here, and I don't know how good you can see it, these red colors to show it to you, we got 2 plexiglass plates. And the reason for plexiglass rather than the cracks, because we don't want to see, yeah? So we put the plexiglass, we fixed the plexiglass at 15 micrometer distance between them. And we actually did here, this is the material coming here, and we did a very low pressure, 2 psi. So, because we know our material actually can flow under gravity, yeah? And we did a very low injection rate, and we with pictures here start looking where is the material. And as you can see, it is this white space of material. You can see it going from here to here. So the material basically flow and fill in between the 15 micrometer plexiglass. We did not test, of course, we tested the cement. You can see the water complete bleeding of the material, but we know actually the cement doesn't go 30 or 40 micrometer. So there is no point of actually trying it at that point. But the material can actually go below. We tested after this to 10 micrometer. The material can flow very well for 10 micrometer spacing. So what we did as well to test how the material can work when you seal with it, we simulated the case with the cement and the steel by taking the steel, putting dry ice inside it. And this is a steel where the cement is cast around. When we put dry ice there, then the steel will actually contract, so it will create a microannulus. And that microannulus, we can, through a permeability test, where we actually close the steel and put this in an apparatus where we can measure the gas permeability, yeah? We can find how big is the average microcrack. And that's what we did here. And you can see in these 2 tests, we've done one where we repaired it with the microfine cement, and one we repaired it with the nano-modified MMA. And you can see the microannulus we created with this dry ice is about 18 micrometers, 18 to 16. You can see 2 samples here, 118, 116 micrometer, very thin microcrack. And we here went and actually injected the microfine cement. And after the injection, we take the specimen and the repair of it, and we leave it to harden. We take it and we measure permeability again. Yeah, and you can see that actually the cement did not go through, similar to what we've seen before. And the microannulus just went down to 12.6. Yeah, so permeability is showing us you still have a big crack. Compared to the case with our material, where the microannulus actually dropped down to 3.6 micrometer. Interestingly, the permeability of, this is gas permeability, of the cement we have would be equivalent to about 3.7. So if you just have the cement, no cracks, and you get this gas permeability, you get 3.7. So that tells us right away that actually you are sealing all the cracks and the flow It's just happening because of the fact that you have a porous cement. We did some work with this with the Norwegian Research Center, and they are very interested in this issue of methane. And they created actually this sample, as you can see, which is very similar to what we talk about, steel, and there is cement in the middle. And they sent it to us, and they said this has about 40 micrometer microannulus in it. So they calibrated it, go seal it, and let's see if you can get the flow rate down. So here we actually, as you can see in the test here, this is a simple pump, and we actually are injecting the material from the bottom here in the microannulus, and you can see our material appearing here on the top, yeah? You can see the material here appearing that's coming from the microannulus from the bottom. In the middle here, sometime we actually put oil so that we can do testing with actually pressures as well. Anyway, and we measured in this specimen and the setup, we measured the flow, gas flow. And this was the gas flow pre-injection, and this is the gas flow post-injection. So basically closed all these micro cracks that was done in it, and we went from 3.8 liter per minute of gas to 0.09 liter per minute. Doing this, we were invited to actually go and test our material in Monterey in Switzerland with a group of companies, British Petroleum, Chevron, Total, and Petrobras, for an experimental instrumented well, where they actually have 20 micrometer cracks in it. And they wanted to see if we can seal this well, which we did here in Switzerland. And you can see this is the water flow in this experimented well. This is the description of that experimented well. It's different chambers, all instrumented. And we went down, as you can see, for the water flow in this from 140 milliliter per minute to about 10 or 7 milliliter per minute. So basically, we completely use our material sealed these microcracks. That actually led, I'm just showing all of what I told you here about in the formation of our startup company, which actually is focused today on doing field work for abandoned wells, sealing abandoned wells. Its name is TS Nano. And up to today, we've sealed about 15 wells in the Permian Basin. Basically, these wells are plugging and abandonment wells where they have significant leakage with methane. And we're using our materials to do this work. And you can see different types of materials we have. We developed over the years with materials that is applied directly and materials that is mixed with cement. So that was the first just example of the nano-modified material we are using to actually tackle a major problem in oil and gas for sealing these against greenhouse gas emission. Going back to our discussion on resilience and thinking resilience, as we were talking with Vedus early about, okay, what would happen? The question usually is, if I have an infrastructure pre-disaster and if there is a disaster happening, now I have a post-disaster bridge. One way we are thinking is of recovery to improve resilience. Yes, so how can I quickly recover? Now, recovery means you are able to restore functionality, not for the long term, but for some time until you actually can rebuild this. So what we were thinking is actually we can use 3D printing to build bridges that can actually be post-tensioned at a fast scale. So idea here is we can model, this is the trapezoidal box girder bridge, and we can model the bridge, we can do the slicing, and we can print it, and then it can be post-tensioned and installed, yeah? Of course, this is a picture with a case where the installation of bridge was a problem, but that's not ours. But anyway, so that's the idea, is 3D printing can allow us to do that fast, yeah? So here I'm showing the case for printing in our lab of this trapezoidal box girder, where we actually, this of course the movie here is running fast, but it's actually can do a cross section that's about 1.5 feet. This is concrete, this is 6,000 PSI concrete that actually can be printed. This cross section can be printed in about 1 hour. So if you want this to be printed and post-tensioned in a bridge, you might be able to print the whole bridge for a short span bridge, maybe a day or two, and you can actually post-tension it and have a temporary structure that allow you to restore functionality. So that is the idea. In the middle between these layers, we have some ideas I'm going to present on actually reinforcing it The main reinforcement here, of course, is going to be post-tensioning for the longitudinal, but we also can add some reinforcement in between. I will talk about it in a few minutes. So this is for the case of concrete, but for with our interest in resilience, we also are interested to look at other materials, which is the case for polymer concrete. And the idea here is that there is a lot of limitations we typically see with cement-based materials. That includes limited ductility, limited bond strength between layers or between other materials, limited durability, especially in harsh environments. So that will get us to use polymer concrete. And polymer concrete, Professor Vibo is one of the national figures in using this material. And it's been used since 1950 in the US, maybe before that. Worldwide also, Japan has been using the material since 1940. Germany, many countries are using it. So we are looking here at how can we progress the use of polymer concrete. And when we talk about polymer concrete, I'm talking about a special type of polymer concrete. There is no cement in it. It's polymer is the binder and mix it with aggregate. That makes the concrete. Okay, so there's no cement in this. There is types of it that use cement, but I'm talking about a type with no cement. So here we are looking at 3D printing of the polymer concrete, and unfortunately these 3 videos are not working. So I am gonna get you to imagine that this basically standard mixer, where this mixing of the material and basically it's fed to this printer, and basically what you see here printed is polymer concrete. And to understand this printing or to examine it, what we needed to study is to study the rheology of polymer concrete, which is basically a rheology and what we call as the green concrete. Rheology is basically how the fresh material works, what factors are affecting it. So we look at the aggregate particle size and distribution and the nature of the shape of the particles. And these two also affect 3D printed cement concrete that you've seen us working with. But the other thing that affects significantly is when you do polymers is the cross-linking about the polymer. So any nanomodification we are doing is affecting that process of the reaction of the polymer, and it affects how fast, how flowable is the material. It also affects the thixotropy of the material, and that's a key factor in polymer in the 3D printed concrete. You need the material to be flowable so you can print it like you see here, yeah. But you need it to be also thixotropic so that you can add layers and it can carry the weight of these layers. So the study here basically is we've done in understanding how the rheology of the polymer itself and how the rheology of the polymer concrete. While the most of the polymers we use, they follow a Newtonian linear rheology, the polymer concrete itself is a Bedingham model, which is nonlinear. But one key thing is, if you would like to print polymer concrete and to use it, is to actually ask the question, can the material carry the load? Yes, can it carry the load axially? And when it fails, how it would fail? In simple, I'm gonna print this area in front of us here, yeah? Can I wait until I reach here again? How fast do I need to print? Yes. So that needs a design. So design of the printing can be done by simulation. And to do that simulation, we have to get the mechanical properties, not of the polymer concrete when it hardens, but with the polymer concrete as it is being printed. So we did this study about what we call as the green strength. The word green here has nothing to do with climate change. It has to do with the fact that it's just fresh and it is gaining strength. So the green strength of the fresh concrete, including it to carry the weight. And what we need to study is we need to study the Moore column fracture failure criteria. So basically looking at this material, say, okay, now this is my structural material and it's going to fail. How can I characterize it? So what we did is we did this shear test of fresh polymer concrete. You see this typical shear test used in geotechnical, where we apply a normal force and then apply a shear force and determine or measure the force that's going to take it to fail in shear, so that we can write this simple equation and get the Moore column criteria, defining the cohesion factor and the angle, the friction angle, the internal friction angle. So to do this, we actually printed polymer concrete samples at 0 time, 30 minutes, 60 minutes, 90 minutes, 110. Why did we stop at 110? Because it started actually gelling and having strength at 110. So we stopped there. And every time of these, we did this test. As you've seen, we applied the normal stress and we actually measure the shear stress. And as you can see here, I'm showing this here because you can't see it on the scale. It's very small. At the 0 time, you have something between 2 to 2.5 kilopascal, very small. But about 110, you have close to 50 kilopascal. So the material clearly is growing capacity with time. Again, this is going to be very important for us to know when are we going to start loading the material, yeah, in both axial and shear. We changed the normal stress or the normal force, and we did the measurement again. So all of these are individual tests. And then we use this to build this relationship between the material, the time, and both the normal to shear stress, and to generate the cohesion and the friction angle. And the way to do it is to actually see how much is this cohesion is happening. And you can see that at to 60 minutes, it's almost zero, very little increase, yeah? But then suddenly we have a jump happening here, and then it starts going linear. So this relationship, we actually can, very important to understand why it happens and to see, to characterize it. So why it happens, first, we can see the cohesion change. We can actually have a function now in time for this polymer concrete to describe its cohesion with time. And we can see that at 60 minutes, that changed. So what we did is we actually went and took the polymer and we did thermal measurement of the polymer, because all these polymers are exothermic. So as the reaction happens, you start getting thermal emissions, yeah? And as you can measure this, you can find what is the gelling time. And using the DTA method, basically, we can get the derivative of the temperature versus time. And you can see here the peak is happening of the derivative at 60 minutes. So that is why we observe actually that change and cohesion in the polymer concrete at 60 minutes. The interesting thing I'm trying to say here is, yes, we can do this, but the more important is we can modify this. That's a polymer as we have it. We can actually modify it to happen at 40 minutes. We can modify it to happen at 90 minutes. And that is where you can do your design for your printing, yeah? And the interesting thing is the friction angle doesn't change almost. It's constant. So our conclusion was that the friction angle actually is not a function of time. It's a function of the type of polymer and materials you are using. Yeah, it doesn't change with time. So using this, we fed this information. Now we have a model or a description for the cohesion and the friction. With time, we can actually model this to actually model the process of printing. Because why? We need to know the stress contours. So now we are printing. This is the polymer concrete modeled in Abacus, where we are actually determining what are the stresses that is happening in the material, because it's important to us to know, given the fact that now we have a more column criteria built with time, we can determine where would it fail, at what layer would it fail, where can I actually, up to what height can I load this material, yeah? So that was the objective, to design the 3D printing process of 3D printed polymer concrete. Here we are basically printing polymer concrete manholes. There is a lot of polymer concrete manholes being built today worldwide. And what we are suggesting is this could be done with 3D printing. And this is again the printing. You can see what we are printing here. We're printing a wall of this polymer concrete. And this is actually the 3D model for it. So we are actually using these measurements in printing to validate our model. Other things we did in polymer concrete is actually start to look at, rather than using a typical polymer concrete, the one I presented here, by the way, this was a polyester polymer concrete. But coming with a question saying, okay, polymer concrete looks better than normal concrete, but can we have some extra ductility in it? So we did this by looking at changing the polymer concrete by using some nanomaterials, and that include aluminum nanoparticles and carbon nanotubes. This is a stress strain of different types of polymer concrete. And you can see the blue one here. This is the neat material. The material have strength. This is in tension. This is all direct tension. Yeah. The material have a tensile strength of 12 megapascal and have a failure strain of about 2%. The interesting thing is using nanomaterials. Here is aluminum nanoparticles. You actually can maintain almost the tensile strength to close to 10 megapascal, but extend the ductility to 5%. So that's a significantly high ductility. And that is just by mixing the aluminum nanoparticles in it. And this is a video of the tension bending tests we do with this polymer concrete. And you can see the bendability of this polymer concrete that becomes very high curvature and bendability in it. And you can see here when we are getting close that that's the material we have. Yeah. So actually in this test setup, the setup is not suitable anymore because you created so much high curvature at the ends. Yeah. That the material, but very high ductile material was close to 5% strain at failure using this nanomaterial. Why does this happen? We looked at the FTIR of this material and they looked why does this, and what happens is that using nano alumina, it actually rearranged the broadened the OH group. So basically it lowered the cross-linking of the material. So that is why we have a little drop in the strength, but we have an significantly extended ductility. Another thing we would like to have is we would like to have this material to be what we call as a smart material. Smart material, a material that actually might help in sensing itself. Yeah, that's the idea of the word smart material here. So we actually used carbon nanotubes in the material. And the idea is to percolate the polymer concrete such that it becomes electrically conductive. And after this, we actually, as you can see, we use the same flexure test, what we have shown early, but then we connected a copper, a silver band on it, and connected this silver band with the device basically to measure the electrical conductivity or electrical resistance, yeah, with time. The idea is the polymer concrete early in its undamaged state will be conductive. As that conductivity drops, you are seeing crack happening in it. And we actually calculated backward two things. We calculated the modulus of elasticity based on the load displacement, and we calculated what I would call the mechanical damage, which is the drop in stiffness. Yeah. And then we went and calculated, we measured the resistance, electrical resistance, and the change in electrical resistance to represent what I would call as the electrical damage, and try to see, does it correlate? Is there any correlation between these two? And to my surprise, these curves, they are very well correlated, but to a level interesting to us. What we did here is we actually, rather than just doing a test, we did a fatigue test. Okay, so when you do fatigue, we always know that you observe in fatigue some primary, yeah, secondary, and then tertiary case, and the material would fail. The interesting one, this is the material with the carbon nanotubes in it, percolated at 2%, and you can see the primary, secondary, and this is with electrical measurement. That's not the mechanical. This is just electrical changes. So the electrical measurement match the mechanical behavior very well. This is the case for neat material. The interesting things with neat material, one, it fails at a much lower fatigue number of cycles. Yeah, that's a material, polymer concrete without the carbon nanotubes. So the nanotubes improved the mechanical behavior and the fatigue life significantly. And you can see there is no change. We can't measure any electrical conductivity because it's not percolating. Yeah. So the material, basically, this polymer concrete can be used to detect the damage and to monitor damage occurrence in the material. Another thing with polymer concrete, we modified it in a different way. This previous one here was epoxy polymer concrete, modified with carbon nanotubes. Here, we decided to actually use some of the repair polymer concrete. So we used the polyurethane. But our interest was actually to do something different. We would like to do low carbon footprint biopolymer concrete. So rather than typical polyurethane, we used a polyol for the polyurethane that has 80% renewable oil. So it's bio-based material. And when you mix it with the sand and isocyanate like classical polyurethane, you actually get this foam, and the material hardens in 1 minute. So that was not going to work for us. We needed to harden fast for repair, but we needed some little time. So what we did, we actually nano-modified the material with multi-wall carbon nanotubes and benzoic acid. And when we did this, we actually managed to get material with no foaming at all. And this material actually have a very good compressive strength. And it actually have a compressive strength close to 30 megapascal, which is about 4,000 psi. And the most interesting was actually taking the material and doing some durability testing by immersing the material in acids compared to typical ordinary concrete. And you can see the polymer concrete do not lose any weight. So it's very durable material, and its setting time went from 1 minute to about 15 minutes. So we actually extended the material, enable it, and it's a biopolymer concrete. And then interesting, if you go look at the, again, the FTIR of it, you can start seeing the changes in the chemistry that happen because of the carbon nanotubes that actually delayed the behavior of the material and stopped the foaming of the polyurethane. The interesting is if you calculate the carbon footprint of this material, you see this is the biopolymer concrete, this is the reference typical concrete, and this is the carbon footprint. So it's basically have about, we reduced 50% of the carbon footprint of this concrete. One way to handle the reinforcing in 3D printing is to actually use what we call as textile in the middle of the printing layers. So to do this, we decided to actually look at how can we reinforce polymer concrete using textile. And to do this, we actually use different polymer concrete, different layers, and we have textile. This textile here was basically basalt fibers. So we put fibers as we printing, yeah? But this case first, we did it without printing. We made the polymer concretes, we tested it with and without the textile. And this is interesting to show you, this is a case with no textile reinforcement. 1, 2, 3, and I'm saying textile because basically we print, yeah, and you put the layer. That's the way we reinforce, rather than putting typical reinforcement. 0, 1, and 2, and 3 layers. And interestingly, this is the red one is the polymer concrete as is, no textile reinforcement. And this one here was 3 layers. You see the significance difference between capacity and the deflection, yeah? And the interesting also is if you look at the crack width, this material would allow, yeah? Because of having the textile. Significant improvement you can have by textile. These videos here, if they work, and it looks like they are working, will show you that actually how the failure of the materials will be happening. So you can see the one that failed already, this one is with 0. That doesn't have anything, it becomes 2 parts, yeah? All the others will keep holding the load, even they are cracked because of the fact that you are using the textile reinforcement. Of course, capacities in the case of textile significantly higher than the case without textile material. And I'm comparing here between what we call as textile reinforced concrete and textile reinforced polymer concrete, yeah? So the polymer concrete textile is way higher in capacity than textile reinforced concrete, which is just the cement concrete with the textile. And the reason is that this crack propagation pattern, in the case of polymer concrete, start to go nonlinear because the material cannot penetrate, so it actually starts going parallel to the textile reinforcement. So you have a significant level of nonlinearity and induced damage in the material because of the effect of polymers. And we wanted to understand why is that. So we took slices, sagittal slices of the material, and we looked under the microscope, and we found that in the case of normal concrete with textile, there is a lot of gaps because the cement cannot actually penetrate the textile. But that doesn't happen in the case of polymer concrete. The material penetration is complete. So with that penetration, you actually have a much better impregnation of the material, so you have a much higher strength. This is the case where we actually are printing and we are putting the textile. So my postdoc is putting the textile. You can think of it in the future, a robot is putting the textile, yes? So, but basically you can reinforce this with another robotic arm would put the textile, and that would make the basically the reinforcement and the for 3D printed polymer concrete. Another use for the nano modification is basically for pultruded bars. We decided that we know that the glass fiber have problems. These problems including its shear capacity, its creep rupture, a lot of these. So how to handle it? We actually built, as you can see here, a facility to do pultrusion in our lab. And you can see the glass fiber and the heated die. And this quick video shows you the process. And what we did, the only difference we did is before we use, in a typical, you take this glass fiber and you get them in a vinyl ester bath, yeah, like this one here. But what we did is we actually dispersed carbon nanotubes in this vinyl ester before it goes. So that's why the vinyl ester looks black, yeah? And that makes the new glass fiber bar that actually incorporating carbon nanotubes in it. So that's the bar, as you can see, going from the die. And you can see the white one is without, yes, that is basically the typical glass fiber. The one here is with the black one is that including nano-modified vinyl ester. And when we do this, we went to do two tests, the tension test and the shear test. Shear is a big problem in glass fiber. And a lot of other properties, all governed by the fact that glass fiber have a low matrix capacity. So we did, this is the tension test. You can see there isn't significant difference in the tension test. Yeah, no one said ever that the glass fiber have a tension problem. Yeah, so we're not trying to improve the tension because tension is governed by the glass fiber itself, not by the matrix. So what we are showing is actually we are similar. But interesting thing we observed when we were doing the tension test. Anyone who did testing for glass fiber, no glass fiber have something, we call it the broom shape. So when glass fiber fail, it shatters like a broom. Yeah. Why? Because the matrix can't hold really well. And you can see what's happening with the case with the carbon nanotubes. There is no broom anymore. Yeah. Then we did the short shear test as I showed, and this is the glass fiber neat, and this is the glass fiber with carbon nanotubes with about 2.5 times the capacity. So once you actually impregnate the material with the carbon nanotubes, you will improve significantly the shear strength of the glass fiber. And we are showing different percentages with different types. And the interesting in nanomaterials is the concept that more is not always better. Because I'm adding the material to modify the polymer. When I add more, it actually starts getting the material to be viscous and not flowing, yeah? And you start having problems with the using of the material. So you can see here 0.5% of carboxylic carbon nanotubes is the best result, rather than if you use 2%. Again, this is chemical analysis we always do to explain why do we have this, and we actually build a model to explain how does the carbon nanotubes hang in one side to the glass fiber surface, and on the other side to the epoxy or the vinyl ester. We use the same thing with a glass fiber composite to see, can we make glass fiber composite connections stronger against shear? The same work, we basically here are simulating an earthquake, that is El Centro earthquake, and we actually trying to simulate this in testing. And this is the joint we have. It's a glass fiber joint, and with neat glass fiber or with glass fiber with carbon nanotubes, and you can see the difference right away. Material have a much stronger shear capacity, yeah? So it actually will not fail. You see the material here in a typical glass fiber and the shear connection fails, yeah? Here it doesn't, material doesn't fail. And again, this is the post-seismic tension. We take the material after going in this seismic test, and we did both seismic tension tests. You can see that the neat glass fiber connection can't take any load almost. The one with the carbon nanotubes actually stay very well and can take significant load after. One last one is we developed recently a bio-inspired viscous damper with nanomodified polymers. And in this case, this is the typical viscous dampers that people use in earthquakes. You can see steel plates with some polymers in the middle. We were inspired by the jigsaw-like pattern that is in many in the human skull, in the turtle shell. Why? Because the problem, as you can see here, is that you are connecting a solid rubbery material to a stiff solid material, yeah? So rather than making this connection with full contact here, we decided to follow that example and to make this jigsaw. The problem, you would say, okay, so how are you going to make this shape? Yeah, so we decided to 3D print it. So we actually made a nanomodified polymer and we 3D printed TBU. And TBU is an elastomer, a thermoplastic elastomer, and we modified it and we printed it and we made that shape, and we actually go and put it in this damper, and we measured the capacity of the damper, and the material is able to damp quite a bit. Of course, there is maybe other materials better than TBU for their capacity, but we actually could see and we modeled it to understand how is the behavior. And the beauty thing about here, you not only are generating, usually in dampers, you want to dissipate energy by material nonlinearity, yeah? The beauty here, you can actually dissipate using geometric nonlinearity. Because of those gaps, you can see that happens during the material being extended, yeah? In tension and in compression. So this is analysis. We just published this paper on this 3D printed damper. This is work very recent about what we call as cognizant composites. And this work basically is focused on trying to embed computing components inside the composites. So we did it by working in actually developing through working with a group in computer science, developing those materials that looks like composites, polymeric shape, but they are actually electric circuitry that can do computation, and embed them inside the composite, and then get them to do sensing and computing in the composite. And what we did here is, you can see this is the typical manufacturing of the composite. And you can see here, this is the sensory material inside, built inside the composite. The nice thing, when the material is similar to the glass fiber or carbon fiber you're using, then it's not going to debond. If you try to put a steel thing inside, it's going to debond, yeah? And we managed it. We actually wrote a code in this little computing microcontroller that's embedded inside, such that when the strain reach a level, that lamp will give us a light. And that's actually the testing we're showing here, where you actually get this LED to show a light once you reach a specific strain in the composite. Now, looks simple, but think with me that this electronic computing unit that's inside the composite, if it can have an AI code. Because if I can have a code to make actually a statement to get a lamp on, I can put a code to actually retract the displacement. I can put a code to actually do some other action, yeah? Because I can actually code inside the structure. That is the work recently we're doing with Air Force Research Lab. So in short, or it was long, not short, we are integrating these interesting technologies, including sensing, using smart materials with sensing, embedding computing components inside the materials, by using very high ductility material to provide this robustness and redundancy, by doing 3D printing so that the material can enable recovering fast, or by doing sensing to ensure how material is damaging over time to improve performance and to increase resilience. And in this graph, we are just discussing about the fact that the question usually, can this be used in reality? Yes, when this can be used in the field. And we're saying there's two things here. There is a market maturity and technology maturity. We see them. I did my PhD close to 27 years ago on 23 only years. Anyway, so on carbon fibers, both tension carbon fiber bars. And at that time, it was science fiction. So people say, why are you doing this? Today, carbon fibers and both tension and glass fiber is used in mini bridges. So there is time where that time the technology matures, yeah? Like 3D printing is gonna mature to become a technology that is actually can be useful, yeah, in the field, and also the market matures so that this price of this technology comes down. And then that will be used, and I'm showing the different technologies we are using, some of them, how mature they are here or here. The same conclusion we talked about, that we presented this work and with the objective of improving the resilience of the infrastructure. Some of the publications we've have in the past few years with the team on these technologies, with the team, with my team, and some of the patents we have of these technologies as well. We definitely acknowledge the funding by those agencies and companies that's been funding my work at UNM for the last 20 years. And I, of course, thank the team that I usually travel and present, get the credit, and they are not. So they do deserve the credit for all this work. And I thank you for your attention.
Thank you so much for a great talk. So I think there is a potential for questions from environmental colleagues and also from the students and civil engineering colleagues. So whoever has a question, like to ask about something particular or general in all the aspects that Professor Taha is working, go ahead, that's your time to do it.
Yeah. Would you like to comment about the durability of your polymer when you are trying to fix the gas leak? How durable it is? Did you do any durability test and how it's bonding well?
Yes, yeah, very durable. Durability issues happens when it happens is with, as you say, with the bond with the cement, because the cement failed before, yes. But mass loss testing, we've done significant mass loss testing with crude oil, with sulfuric acid, hydrochloric acid, ionized water, many of them. Material usually mass loss has been within 1%, which is the resolution of the measuring devices we are having. But of course, once you start having the interactions, actually, in many cases, the part that is failing in the compound, when you try to do slant shear tests of samples, small samples have both the cement would be actually failing. So you wouldn't be able to test post-exposure, because of the exposure to this aggressive environment. But the material is extremely durable. And we have two materials. I'll present here one. We have another one that can be actually mixed with cement for new plugging and abandonment. Very high durable and high temperature material.
So what was the temperature range you are studying?
This one, the material I presented here, have a temperature range of about 150 degrees Celsius. The other material mixed with cement have a temperature range of 330 degrees Celsius. So wide range, so that you can, because as you know, it depends. Usually P&A, where the material applies, is what we call it close to the surface plugs, which is within the top 2,000 feet. So temperature doesn't go there above 50. So the materials is very well for that. But the other material that can be used actually for plugs and for balanced plugs up to 350 degrees Celsius.
Thank you, Dr. Before there was one more.
Yes.
Yeah. Question about the point you said, polymer concrete almost do not lose the weight. So what test did you use to?
Yeah, do not lose the weight, like what I'm answering here, Professor Vibu, about the durability test. So what we do is basically in durability testing, you take samples of the materials, and you immerse them in aggressive environment, like hydrochloric acid, or sulfuric acid. And by the way, sulfuric acid, usually the most aggressive is about 10% because it's oxidized. When you if you put cement, you might not be able to get the material, because it would be completely dissolved, So that's the mass loss. We measure with time how much of the material remains. In polymer concrete, the material, because again, as I'm saying, the main application has been for many of these materials is manholes. So it's very high temperature and acidic aggressive environment. So polymer concrete do not lose. Most of it, of course, for bare application, you need to select the right polymer. But the ones we used for this do not lose weight.
Can we use it with the cement? I mean, polymer with the cement.
You can, but if you combine the polymer and cement, then you are going to a different type of polymer concrete. We call it polymer modified concrete. That's a different type of material, different properties. It depends. Yes, there is application polymer modified concrete for it is good, but the focus we have is the polymer concrete, where we are not using cement. Material, as I said, very useful for repair applications. Lots of time polymer concrete is. Also for bridge deck overlays, polymer concrete is used. There's many applications. ACI Committee 548 has been working on polymer concrete for 70, 80 years. So it's, and again, there is with cement and without. The most common today is the one without cement.
But let me add to it, because I think you're a student, right? In general, when you speak about concrete, like when I'm teaching, you always associate concrete with aggregate cement and earth, right? So there is always this element of water, because you need cement solidarity, right? In this polymer concrete, as I understand, there is no water involvement at all. It's basically polymer with polymerizers, and then there is an aggregate, like you would put normal aggregate to it. So there is no water involved because you are not using any hydraulic binder whatsoever. Yes.
And the material typically, of course, is more expensive than cement concrete, But this is why we select the application we do it with, The material is typically, this polymer concrete is impermeable. Cement hydrates, and then you make porosity with the hydration. Polymer concrete doesn't, it polymerize, but typically the material, especially if you have a good mix design, the material is impermeable. We actually tell people because people in the Department of Transportation sometimes say, okay, we would like to measure the chloride ion permeability of polymer concrete. Tell them you might damage your machine because you cannot transport chlorides, yes, because it's a polymer matrix like plastic, correct? So
Also, I have a question about the sitting time.
sitting time, yes, yeah.
Is it 18 to 15 minutes to set, right?
Not all polymer concrete. That's actually the fastest one we use, which is the polyurethane. Polyurethane is a very fast. It's very good for repair application, especially if you want the material, if you would like the material to catch stress quickly. Yes, you don't have a lot of time. Polyurethane is good for that. But we actually, the case I presented for the polyester, we extended the time to 2 hours. Yeah. Typical polymer concrete sitting time is within an hour, 45 minutes, an hour. And the nice is polymer chemistry. So we can actually engineer the time. We can get it to do faster. We can do it to do slower. But usually somewhere between 45 minutes to about an hour and a half. So polyurethane is a special animal. It's just used for the fact that it is fast set and gets strength very quickly. Yes.
Thank you for your excellent presentation. I had a few questions. So one is, in general, when you're selecting your monomers for your mix, what is the inspiration for that? Is it mostly driven by your application? And if so, how do you go about selecting monomers that meet your need?
Yeah, I think you answered the question. You give me a hard question and you answer it. It is driven and inspired by the application. So if I'm doing a repair, job that where I actually want the material, I want to apply forces quickly, a material or a polymer like polyurethane will be the choice, yes, because it can harden very quickly. If I'm doing a bridge deck and I'm covering all the bridge deck with a polymer, I need a reasonable time to get the crew to actually apply the polymer and maybe broadcast aggregate on the top of it, yeah? So driven, that's one. So the selection, I wouldn't try to modify polyurethane on the bridge deck, correct? Because that's way too much. But I can try to modify the methyl relate on the bridge deck because it's getting hot, so I'm gonna modify it with materials to actually extend its time. So it's driven by the application, like what I showed in the case for the well work. The application was driven by a few things. One of them is very high flowability. So if I use epoxy, which we try to use, it doesn't flow in. It's become, it can flow, doesn't have the contact angle to flow. So now I'm excluding all the family of polymers with high contact angle. Yeah. Compared to a case where I'm doing 3D printing, polyester concrete was good, but polyester wouldn't work for the well. So the choice is driven by what is the main criteria in the application that dominates. But I can do also optimization, yes, because as we were discussing, what about the durability of the material? I might choose a material that flows very fast, but doesn't have strength, doesn't have stiffness, is not durable, doesn't work. So you need to meet the key criteria of interest. That's what drives the selection of the bond.
And then I had another question.
Yes.
You spoke about the polymer concrete being able to reduce the carbon footprint.
Yeah.
But is that in general, what are the scenarios where that is the case, and what are the scenarios where perhaps competition is higher? How are you?
Very nice question. So the answer, it depends how you calculate. Okay. So typically, if we just calculate carbon footprint of the material as we are using it, yeah, polymer concrete, polymers are driven from hydrocarbons, yeah, so they have very high carbon, correct? So if I calculate 1 kilogram of polymer concrete to 1 kilogram of cement concrete, polymer concrete have a higher carbon footprint. However, which we prove, and it's proven in the literature, these polymer concrete have a service life way longer than the concrete, cement concrete. So if I account for the service life in the polymer concrete calculation, it has a much lower carbon footprint than cement concrete. Yeah. So it's a choice. How are you addressing the problem of the carbon? Do you calculate the material considering the fact that when I cast a polymer concrete tank for a manhole, This is supposed to last 100 years, and actually it might last longer. I might get rid of it just because the building is going. Yeah. Compared to cement concrete, where we know 20 years and it's going to be gone. So this other material will have a lower carbon footprint. So it depends, but typical calculations, hydrocarbons, of course, result in a higher value for carbon footprint. Here, it was lower because we did not use hydrocarbon. For our polyol, we used actually an oil vegetable material that is sustainable with a low carbon footprint. That's why we managed to drop it. And this is not calculated based on a life cycle. It's calculated based on just values for that's lower than the cement concrete. Yes.
When you talked about rheology, are you studying the cross-linking of the material at the microparticle level, especially from the chemistry point of view?
Of course, we have to. But when we talk rheology, rheology doesn't relate to studying cross-linking first. Rheology, basically, we look at the polymer, we apply a shear stress to the polymer, we basically shear it, yeah? Different shear rates, and we see how does the material thicken with time. Yes, as you keep applying the stress to it. So the effect of time and shear stress on the polymer. That's what describes the rheology. Now, to explain this, yes, one polymer to the other behaves differently. To explain it, we go back to the polymer and study its cross-linking and study its rate of polymerization. And when we do this, of course, with FTIR or TGA or DSC tools that do microscale chemistry analysis. Yeah, but rheology itself is a macro scale test. So we use the microstructure analysis and chemical analysis to understand, okay, why did the glass fiber behave better? Yeah, well, it bonded better. So how can you prove this? Well, we take the polymer and we do the FTIR, and then we found those links. Yeah, so found these peaks. So it tells us, oh, there is carbon links here and there is chemical links here. Now that explains to us why the glass fiber did not shatter in a boom shape like the typical glass fiber. So we use this to explain the mechanics we are doing testing.
So let me add to this, if I can.
Please.
Question. You presented your test basically more Coulomb criteria,
Yeah.
criteria, simple test from geotech that we know from the soil mechanics.
Yes.
But you could also get similar information or even more quantification and understanding by doing the rheology test in the rheometer. Is there any particular reason why you choose this method not to go to the rheometer when you
Yes.
epoch over time, epoch over temperature, epoch over shear rate? Even though you know that, okay, it behaves as being
We published about exactly what you talking here about, the effect of the rheology and rheology change with time. We did publish about this, and we did it exactly this way. Very difficult to extract this to the green strength. Why? Because I am printing a structure. So to do the printing, I need the rheology measurements. Yes, so that I know what's the flowability, what's the thixotropy, this is all rheometry. But the minute I printed the material, and now I'm doing this big cycle, and I'm coming here in 30 minutes, my question is now, what's the shear capacity of this? Because remember, the printer, when you are printing, actually do some friction, yeah? So with the fail in shear, how much in 20 minutes, how much capacity can it take axially? Rheometer wouldn't give me this yet. So rheometer data is absolutely necessary to do the printing parameter, the thixotropy, the buildability rate, all of this. But to actually to do the mechanics of the concrete, rheology would not. You will be extrapolating a lot. So that's why we went to that way. And then the paper, we have this paper in review now in construction building materials. We have actually the first part of it is rheology measurements. We're describing all the rheology, the thixotropy of the material, but that is up to time zero. Because the minute I place the material, that's time zero in my calculation, yeah? So now how the material is behaving from this is why we did this mechanical test.
So on those graphs which presented time 0, time 3 hours, etc., those are all, you engineer the time to reach the solid state after those 3 hours, and then
yes, this is the time where you actually did the test, so that you already have the material is extruded already.
And is it already?
And now from that extrusion time, yes, I'm measuring the time. So when I say 110 minutes, it's from the time I extruded the material, not from the time I mix it. Rheology time is from the time you start mixing. Yes? Here I'm not doing rheology. I'm doing from the time I extruded the material, I'm measuring the time. So I did here actually testing for different materials. They are not the same material. Yeah? They are different materials, every one of them. Here, for example, this is the material extruded, and I took the sample, and then I take it to the shear machine, yeah, at 0 time. Then another one, I waited, and then did the test at 30 minutes. Then another one, I waited and did 60 minutes. So I'm waiting. I extruded the material and kept it for 60 minutes. Then I went and did the shear test. That way I can, and I did them at different normal stress, 2 different normals, so I can actually extract this relationship with time. Does that make sense?
Yes, it does. Okay.
Yeah.
More questions? Okay. So thank you so much, Professor.
Thank you. Should we stop?
Amazing work.
Thank you.
In 30 minutes.